Here we have a problem that utilizes modeling. That's a modeling question utilizing quadratic functions. So if we read the first thing we always want to do when we have a word problem such as this is, of course, obviously, to read. To read it, not just to read it, but to understand. And that's probably the more difficult part, is understanding what we're reading. And we need to do more than just understand. Particularly, we need to be able to translate these words and phrases into mathematical concepts, equations, and such. Okay, so we have the flight of a baseball after it's been hit from an initial feet of 4 feet above the ground. And this flight of the baseball is modeled by a function. And this function is a quadratic function in nature. So this is a quadratic function. And we see how useful quadratic functions are because they're quite natural in explaining certain physical phenomena, particularly after you throw a ball or hit a ball, right? In the air, the flight of that ball, the trajectory which that ball takes is parabolic. And there's the physics that can explain the reasons as to why such a ball goes through this parabolic trajectory. But we're just going to consider that we accept it. We accept the fact that the ball will follow a parabolic trajectory, and that parabolic trajectory can be graphed by this particular quadratic function. So then, once we understand that, then we need to be a little mindful as to what these symbols, numbers, letters represent. So particularly, it's saying h of t, which is the output value of my function, is the height of the baseball in feet. So feet measures distance, and we're measuring the distance above the ground, which is the height. After t seconds, after t seconds of being hit, right, of being hit. Okay, so we need to be able to decipher all of these letters in their respective meaning in the context of the problem, because all of these letters will mean different things in different contexts. So we need to be able to be very familiar with the context that we're given, which is a ball in the air, right? So now we want to find the following things. This is a very typical number of questions that pertain to this kind of scenario, right? So first we want to find the time it takes for the ball to reach the maximum height. We then want to find what is that maximum height that the ball attains in its flight or in its trajectory. And finally, we want to find how long it takes for that ball, baseball, after it's hit, to come and hit the ground. So the first order of business we're going to do is to understand this quadratic function, right? Sorry about that. This is the quadratic function that we're looking at. Now, maybe we don't know exactly what it looks like, and this is when we can use our calculator to give us just an idea of what it's going to look like. So if you have a graphing calculator, I have a TI-84 plus CE color edition. So I plug it in my y equals, I plug in this guy, and of course, this is in terms of t, but here we're going to use in terms of x. It's not really going to affect much. So when I graph it, right, if I were to graph this, I get this kind of graph. And I should make this not an x, but a t, because my function inputs time, t. And this time is in seconds. We also have the height, which is in feet. Now, if we understand this quadratic a little bit further, right? It says that it's been hit when it's 4 feet above the ground. Now, how is this significant with this how does this correlate with this function that they give us? Well, if we look at this function, it's a quadratic. If I want to find what's the height at the initial time means that my time equals 0. That's what the initial time is. It's when t equals 0 in this scenario. So if I were to plug in t, 0 for t here, I would get h of 0 equals, this whole thing would be 0 because if I plug in 0 squared, 0, 0 times 0, 16 is 0. Anything multiplied by 0 is 0. 75 times 0 is 0. So this is 0, and what's left? It's 4. So far this coincides with this initial height that the ball has. So my initial height here, which is another way you can think of this, is as the y-intercept or the vertical intercept, right? This is 4. So really, I don't care about anything before it was hit. So the quadratic, even though the actual parabola continues on, right, forever and ever and ever, theoretically, in real life, we're just considering this portion of it all the way up until it hits the ground. We're not considering the fact that this continues going down into the earth, because it doesn't. It just hits the ground and boom, it stops. So we really only care about this portion to this portion of the graph. Okay. Great. So now we have a better understanding, right? Now let's look at the first piece that we're looking for. It says find the time it takes, and also we have to understand that this is in nearest hundredths. So we're going to have to round once we get the answer. So it says find the time it takes for the ball to reach the maximum height. So what does that mean? What's another way? So this is another thing that you should learn as a skill, is to say something in another equivalent way. And this is what we do a lot in these type of math problems. We try to find what's another way, maybe a better way, or maybe a simpler way to explain or to understand a certain expression or a certain sentence, right? It says, find the time it takes for the ball to reach the maximum height. Well, my ball, this ball, baseball, undergoes this parabolic trajectory. So I can say to myself, what is the time that it takes for the ball to reach the maximum height? But if I look at this, I know that the maximum height is given by what's called the vertex. This is my vertex. This is the maximum height. And this is a maximum height of a parabola. And I know it's going to be a maximum even without even graphing it, because the leading coefficient of this quadratic is negative. And since I know it's negative, I know it will be a maximum. The vertex will be a maximum. And this vertex has coordinates. It has a t coordinate and an h coordinate here. And this coordinate is found if I were to find what's called the axis of symmetry. The axis of symmetry is a vertical line that divides the parabola into two equal halves, and that goes right through the vertex. So whatever the axis of symmetry is, that will be the x value, or in this case the t value, of this parabola. And how do we find that? So this is going to be the first thing. So what I'm trying to say is, the first part of this problem is really asking you, without actually saying it, find axis of symmetry. So we have to be able to understand the context of the problem and relate it to something we already know. We already know about parabolas. We already know how to talk about parabolas, how to find the parabola, the y-intercept, the x-intercepts, and the vertex, and the axis of symmetry. We know how to do that, almost like robots. But now we have a problem that doesn't exactly ask us, find the axis of symmetry. It just tells us something that we should be able to find out. And it just so happens that what we're trying to find out is exactly the axis of symmetry. So the axis of symmetry is given by a formula In this case, it's going to be t, not x, because we're dealing with the input. The independent variable is t, or time in this case. But still, it's going to still be the same, negative b over 2a. So I want to find what negative b over 2a is. Great. Now how do I find this? Well, the good thing is we have a quadratic function, and it's in a polynomial format. So I can read off what a is, what b is, and what c is. Because usually we have a quadratic in the form ax squared plus bx plus c. I have it. In this case, it's a t squared plus bt plus c. But my a value is associated with the variable with the squared term in it. So a will be negative 16, and so on. B will be 75, and c will be 4. So once I have this, now I can plug it into this formula here, and I get negative 75 over 2 times negative 16 is negative 75 over negative 32. And if I plug this in my calculator, and I want to find what that is, I get positive 2.34375. But I want to write this in the nearest hundredth, which is this 2 decimal places to the right. This is the 10th place, this is the 100th place, this is the 1000th place. So I'm going to look at the 1000th place to see whether I round up or if I just keep it the same. Well, this 3 is below 5, so I keep this 4 the same. So actually, my axis of symmetry, t, is 2.34, rounded to the nearest hundredth. Now what does this mean in the context of the problem? It's exactly the time it takes for the ball to reach the maximum height. So this t value here is approximately 2.34. So you would say, in words, after 2.34 seconds, the ball, or the baseball, reaches a maximum height. So we found it. We found part I. And we're done with part I. Now how does the part I tie in with part double I? It says the maximum height that the ball reaches. What is that maximum height? Well, I found the time it takes for the ball to reach the maximum height. In other words, I found the input value of this function that would give me the output value, and that output value would be the maximum height of the ball. So far I know what the input value is, which is 2.34. I want to find the corresponding output value. So this is, I'm done with part I. So I have 2.34. Now double I is asking me, find the maximum height of the ball that the ball reaches. So in other words, I'm trying to look for what's the output value when input value is t equals 2.34 seconds. That's what they're asking me. Basically, I'm trying to find what's the y coordinate of my vertex. So once I find the x coordinate, or in this case the t coordinate of my vertex, I just need to plug it in to my function. And remember, if you saw the previous, what I erased, I had that t was equal to negative 75 over negative 32, which is the same thing as saying 75 over 32, which is approximately 2.34. Now, this is a rounded answer, so I'm just going to keep it in exact form. This is exact form. This is exact. And this is an approximation. So I'm going to keep the exactness and then round after. So I can actually just plug in 75 over 32 because this is exactly the time it takes. This is just a rounded answer. So I'm going to plug this in. And if I want to plug this into this input, into this function, I would have to do negative 16, 75 over 32 squared plus 75 over 32 plus 4. Now, when you plug this in your calculator, you can do that, and it might take some time to plug it in your calculator. And the problem with that is that there may be some error when you, if you were to put everything correctly, no problem, but there might be some times that you may forget the parentheses, right? And so just to make sure, after you do the calculations in your calculator, you can actually, if you were to graph the function, which you have it here, if I want to graph this, I can actually use second trace and use the function value, press enter, and it's asking me, give me an input value, and my input value I'm going to put is exactly the input value that I found, which is 75 over 32. Then, when I press enter, it's going to give me a corresponding output value. So the corresponding output value that I found was 91.890625. This is the corresponding output value. So this is going to be 91.89 dot dot dot. And so then the coordinates of my vertex will be 2.34 comma 91.89. But what does this second coordinate represent? It represents the height, the output value of my function. And I want to round this to the nearest hundredth. So then this is going to be approximately 91.89 feet. Because this 0 here means that I'm going to keep my hundredth place the way it is. So then we would say the maximum height the ball reaches is, the max height that ball reaches is 91.89 feet. So we did part double I as well. And we can also do this in our calculators by using the same second trace, which is calc function. So this is a very useful tool, second trace, which is the same thing as saying calc on your TI-84. If you have another function, graphing calculator, I'm pretty sure they have other kinds of functions. And you can use calculate, and you would be able to use the maximum function, right? So we have a maximum function, and it asks us what's the left bound, right? What's the right bound? So this will be like the left bound. And this would be a right bound. So you always want to move that cursor a little bit to the left of where your vertex is and a little bit to the right of where your vertex is. Make it guess for you, and you get the same numbers. So you just have to be able to know what the significance of those numbers are in the context of the problem. And if you know what those numbers represent mean, then this problem isn't much of an issue. So we found that the time it takes for the ball to reach the maximum height is 2.34 seconds. And we found that the maximum height that it actually achieves is 91.89 feet. So we did part I and double I. Now for the last part. So I can erase this portion here. Now for the last part, it's asking us how long it takes for the baseball to hit the ground or to be back at ground level. So the word or the phrase how long indicates that we're dealing with time. So again, the word is what's the time, but we're asking what's the time that it takes for the ball, the baseball, to not get back to the height, the maximum height, but when does it actually hit the ground? And when we say hit the ground, we mean that our height equals 0. That's what it means to say it hits ground. And you see how we translated this sentence or this phrase, hitting the ground, to represent that the output value of my function is 0. So being able to translate the words into equations is a supremely necessary skill to master. So this is going to be the third part of this problem. So really what I'm looking for is solve, mathematically, is solve for t when h of t equals 0. What's h of t? H of t is this function that we have that's given to us. So I'm really saying what's negative 16t squared plus 75t plus 4 equal to 0. I want to solve for t. But really what they're asking us is, can you solve marker doesn't work. Can you solve quadratic equations? So all this time that you've been learning how to solve a quadratic equation by factoring or by using the quadratic formula, right, was so that you're able to eventually get to something with a little more significance to it, a little bit more meaning to it. It's not just solving an equation just to solve the equation, but this equation now has a physical meaning that can actually give us more understanding to other things, not just to baseball, but to other physical phenomena or other things that require or can use quadratic functions to model them. And how do we solve this such a thing? Well, we know how to use the quadratic formula. That usually works. So use quadratic. So when we use the quadratic formula, we know that it's negative b plus or minus the square root of b squared minus 4ac all over 2a. And all we do now is plug in the values accordingly. My b value is 75, so I get negative 75 plus or minus the square root of 75 squared minus 4 times negative 16 times 4 all over 2 times negative 16, right? And so then we have to continue with this stuff inside here. And if I plug it in my calculator, and I think I already did that, I think I got 5881. So I got 5881 here, all over negative 32. And we know that we're going to get two solutions here. We're going to have the plus version and the negative or the subtraction version of these two solutions. So if I were to do that, so if I'm going to add the two of them, so this is going to be one of the solutions. If I add negative 75 with the square root of 5881 over negative 32, I get negative 0.05 ... right? I get negative 0.05. So this is going to be somewhere here, right? But what did we say in the beginning? We don't care about anything that comes before t being equal to 0, because we only care about after the ball gets hit, not before it gets hit. So this solution here we actually don't use. We can say we reject it, right? We're not going to use this because in the context of our problem it's not relevant. So the second guy, if I evaluate it and put it in my calculator, I get 4.7402 . Now this is going to be this t value here. And of course I'm rounding it to the nearest two decimal places, the nearest hundredth. And because that 0 is the thousandth place, that means I keep that 4 the same. So the ball hits ground after approximately 4.74 seconds. And we're done. We're done with part III. We could also have done this problem, this portion of the problem, graphically. And since we have the graph, and sometimes in your graph, because it's such a big graph, 91 in height, and it's kind of not that wide horizontally, you may have to change your window accordingly, so you'll be able to see the whole graph. And you can just go to window and change the x min and the x max and the y min and the y max in order to resize your window so you can see the graph in its entirety, or at least the portion that you're interested in. And then once you have this graph, there's actually a function here that you can use. Again, you use second trace, and it's calc, and you go to 0. And again, we're going to use this idea of left bound and right bound. So I'm going to use the left bound, which is a little bit to the left of my point of interest, and the right point. And we're going to use the 0 function. This is called the 0 function because this is also known as my 0. That's when the output value equals 0. So when you press the left bound and the right bound, and you make a guess, you get this answer. You get that the answer will be 4.74000, and then the y value or the output value would be 0. So this problem can be solved algebraically, graphically, with your calculator, in more than one way. Hopefully you see now how useful knowing quadratic functions is, because it can help us understand physical phenomena that we might be interested in. So I hope this helps.